Welcome to the Geotalk. This afternoon we welcome not our newest staff member, but one of our newest staff members who joined us last year for his first Geotalk in this room. And that's Matthew Brayshaw. And so Matthew hails from KZN. He was an undergraduate and a PhD graduate of UKZN. And for his PhD, he worked at Rosh Pinah, and that'll be the topic of his presentation this evening. But after working at Rosh Pinah and getting his PhD there, he moved on to Geita Mine in Tanzania, where he was working on structural controls of gold mineralization. And now he's doing some work in the Cape Fold Belt, so hopefully we'll hear some more of that research in the near future. And he's also going to give a talk in Zulu, in which he's fluent. No, he won't. I'm just kidding. All right. But he could give a talk in Zulu, I guess. So Matthew, thank you very much for your first Geotalk, and over to you.
Sanibonani nonke namhlanje. Igama lami nguMatthew Brayshaw, ngivela kwaDukuza, KwaZulu Natal. Namhlanje ngizokhuluma ngezinye izinto. I'm just kidding. Okay, so thanks very much, Grant, for the introduction. The title of this talk is the title of a paper that was published last year on my PhD work. So procrastinated quite a lot and took quite a while to write it up and eventually publish it. That's why it was only published last year. And so, yeah, sorry if this is a little bit long because I'm trying to fit quite a lot of information into one talk. So hopefully we'll keep it to like an hour. But yeah, so the structural evolution and architecture of the outer margin of the Gariep belt at Rosh Pinah in southern Namibia. This is Rosh Pinah town over here, and the mine is on the side of the mountain here. Basically, you drive into the mine, and that will edit there. And this was my field area, this Rosh Pinah mountain, and the mountain to the east of that, the Macmillan's mountain. So for those of you who don't know where this is, in terms of a regional geological setting, the Pan-African Gariep belt, it straddles southern Namibia and northwest part of South Africa, stretching from Lüderitz to Clencia. It's this arcuate northwest trending belt, about 400 kilometers long, about 100 k's wide, and it abuts against Mesoproterozoic basement, the KwaZulu-Natal province. And this is basically what the Gariep belt looks like in terms of the regional picture. In pink here, we've got the basement rocks to the east and to the north, and everything in grey is the Gariep belt. The Orange River is here, so that's basically that's the border between South Africa and Namibia. And there's two major terrains, quite different terrains that make up the Gariep supergroup, now exposed in the Gariep belt. The Marmora terrain, this is shown here in dark grey. That's oceanic terrain. It was basically three terrains that amalgamated intraoceanically. And then we have to the east of that, in light grey, we've got the Port Nolloth zone, which is a volcanosedimentary sequence, which comprises the Port Nolloth group. And this is a big thrust zone, that the Shuckelsberg thrust that separates the two terrains. The belt was formed by a sinistral transpressive event, and that's really what I'm going to talk about today. But just backing up a little bit, looking at how the sedimentary rocks and volcanics and everything, got formed in this this basin, which is then deformed. Well, from 770 to 720 million years, there was this crustal extension within the Western Kalahari Craton, which is tried to show over here, with this Gariep rift. And in it, sediments were deposited, which basically formed the lower part of what's known as the Port Nolloth group, as well as some rift-related rhyolite. And then basically that was a failed rift. It didn't really carry on and form a proper large ocean. But this failed rift was later reactivated from 650 to 600 million years. And some oceanic crust was formed, which is actually what comprises the Marmora terrain. And so some new sediments were also deposited at that stage. And this is known as the Marmora Back Arc Basin. And then getting into the deformation, an inversion from extensional to compressional tectonics occurred 600 to 580 million years. And at 575, the Marmora terrain was accreted to the Port Nolloth zone. So I've just tried to illustrate that here in dark grey. We've got kind of these naps here. So Marmora terrain being thrust over this Port Nolloth group. And peak regional metamorphism was around 545 million years. And so this is just a kind of a schematic cross-section of basically what we have now in the Gariep belt. With the basement, with this sole thrust here, Port Nolloth zone exposed in the east. And that's going to be the subject of the talk today. So, basically, we know that deformation didn't last longer than about 510 or something like that, because of these post-tectonic plutons that intruded, dated at around about 507. All right, so just zooming in a little bit into the Port Nolloth zone around the Roche-Pinard region. It's important to set the context and to say that the Port Nolloth zone it's quite complex structurally, and it's been subdivided into two zones, an inner and an outer zone. And so here we can see the basement again, and we've got an outer margin and an inner margin separated by some very large-scale faults, and really the difference between these two zones are the structural styles. The structural styles of D1 and D2 structures. And so the study area is located the southern extent of the Roche-Pinard Mountain and also Macmillan's Mountain here, with the mine just over there. And it's bounded by the basement cover sequence contact and what's known as the Ice Road Fault, which extends all the way down this valley here. So I'm literally going to be talking about that small area there. It's sort of like 8 by 4Ks. Sorry, wrong direction. Okay, so that was just setting the context. The aims of this study, well, previous workers had mapped this part of the Gariep belt in like 1 to 10,000 scale. So because I'm a bit of a perfectionist and I love field mapping, I decided to map it at 1 to 1,000 scale. And so the aims were to produce a really detailed map and then work out the 3D structural architecture of this outer margin of the Port Nolloth zone, as well as determine the structural evolution through overprinting relationships, determine the strain variation across this zone, as well as propose a tectonic model of deformation that will account for the structures and the strain. All right, so just looking at the geology of the outer margin of this Port Nolloth zone. So here's the Port Nolloth group. This is kind of like a strat column in a sense. Well, the formations that are exposed in the study area are these lower formations, lower and middle formations of the Port Nolloth group. Right at the base, we've got this Lacusson formation, mainly cross-bedded quartzite with some carbonates. Frederfontaine formation, it's quite a thick siltstone package with some interbedded limestones. Kaukaus Formation is a diamictite. Then the Rosh Pinah Formation. Rosh Pinah Formation is economically important for lead zinc mineralization, which is what they're mining there. But it's basically a sequence of turbidites, arcos, and thinner argillite beds with some rare mineralized carbonates, some dolomites, some conglomerate lenses, and also some felsic volcanic rocks. We've got the Volacral Formation, which is a listostromes, so it's like these marine sort of debris flows, and then the Spitzkopf Formation, which is mainly rhyolites. All right, so in terms of large structures in the area, we've got 10 large-scale antiforms and synforms with half wavelengths of about 10 to 100 meters. Well, large is a relative term, but so the folds on this Rosh Pinah mountain here all verge towards the southwest. So they verge in this direction, moderately dipping axial planes, whereas the folds on this Macmillan's mountain here are upright. They've got subvertical axial planes. And the main formations exposed across these mountains are separated by these very large north-northwest striking faults, formation-bounding faults. So looking at some simplified geology of the Rosh Pinah mountain here, this light yellow is arcos, argillite, so that's mainly the Rosh Pinah Formation exposed on the mountain. Down in the southeast, we've got the Volacral Formation, so some argillites and these listostromes. And then to the east of this mountain, the Spitzkopf Formation, which are chiefly rhyolites, and this late Jurassic dolerite dike, which cuts through everything. The dashed lines are contours, so the base of the mountain about 400 meters, the top of the mountain about 850, so it's like 400 meters elevation. We've got some axial traces of some of the major folds plotted on here, and a couple of bedding and cleavage readings as well. And just take note here of A and B, which is a cross section which has got a bit of a kink to it. Here we've got the cross section across the mountain. And you can see the folds all verge towards the southwest. And then we've got out towards the east these rhyolites of the Spitzkopf Formation, which is fault-bound. There's also this quartz sericite schist, which cuts across one of the synform hinges. But most of the folds are southeast plunging. They verge towards the southwest, and then there are these kind of odd-shaped folds that verge. They're kind of like Z-shaped folds which verge towards the southeast, and we'll speak a bit more about that and their significance. Macmillan's mountain. This is simplified geology of that mountain. Again, we've got the Rosh Pinah Formation exposed in the west. The highest relief, the most resistant sort of part of the mountain are these is the quartzite-dominated sequence of the Lacuson Formation. We've got the siltstone unit with some interbedded limestones as well. And then out towards the east, we've got this diamictite unit. Two very large faults, formation-bounding faults, the Rosh Pinah Fault and the Klipnius Fault, which extend down through the mountain there, and some axial traces of the folds as well. So that's, let's just go back quickly, a cross-section C to D. So you can see clearly that the folds are upright, they're not verging in any orientation. Folding in the Rosh Pinah Formation, some folding in the quartzites with interbedded carbonate units. This large Macmillan's anticline, the diamictites off towards the east, So I'm going to just discuss the different structures and categories according to their age, starting off with D1 with accompanying S1 fabric, D2 which is the most recognizable event with strong cleavage, S2 cleavage, and D3 which is recognized by deformation of the S2 cleavage. Okay, D1 structures, not very widespread, they're quite localized in terms of just recognizing them in the field. So this photo here is like a carbonate sandstone and a massive carbonate over here. You can see the bedding contact. And the F1 folds are these folds here, and we've got an S1 fabric over here. Well, actually it's the S1 fabric which is most recognizable from this outcrop. And then we've got this undeformed S2 cleavage which cuts across it. But these type of cross-cutting relationships are quite rare, only sort of really exposed in certain areas. Another example on Macmillan's Mountain, we've got this dolomite unit which is encompassed by this pink carbonate, less competent material. So this unit has been folded quite tightly. You can see these stigmatic folds. There's been some sinistral shear here, deforming this unit, and you can see S1 being deformed there. So really, the D1 structures are quite localized here and there, not so widespread in terms of being able to be recognized. D2 is just pervasive everywhere. Most of the large folds in the area are D2. So the S2 fabric that corresponds with that is a penetrative cleavage, a space cleavage, and this is F2 fold in the Volacral formation. This is an Arcos unit which is thinning and it's been folded, and you can see this S2 cleavage very pervasive in the argillites that encompass this unit, and then some quartz veins have exploited the cleavage in the Arcos. So that's really what it looks like in the field. The Roche-Pinard formation, got these turbidites, so we've got these thick Arcos beds, nicely folded. I've got some very thin interbedded argillite there. And on one part of the Roche-Pinard Mountain, we've got this alteration zone, which is a quartz sericite schist that cuts across a synformal fold hinge. So here's your fold hinge here, and that's basically the boundary between the alteration zone and the unaltered Arcos. Sorry. More D2 folds on Macmillan's Mountain, some limestones, dolomitize limestones, siltstone sequence, some nice folding there. So because the folds are non-cylindrical, I subdivided different folds, basically subdivided different parts of each axial trace into subdomains in order to plot up the poles to bedding and work out the fold plunge. So that's what this map shows here. So you've just got the traces of bedding in different units, and these blocks are subdomains, and the number with the arrow represents, so it's the fold plunge reading, and the arrow represents the trend. So for a fold like this Roche-Pinard antiform, what you see here is just a number of subdomains along the axis of the fold, and so you can see the fold plunge changing from 15 to 20, 40, 30, 15, 20, 26. So really the same for all of these different folds. This is the ridge synform, for example, different subdomains. So that's what this map is trying to show. So you can see that majority of the folds plunge towards the southeast. And when we plot all the cleavage for this Rosh Pinah mountain, the S2 cleavage, it plots in a cluster, which with an average of a 340.52. And another thing just to note about this map quickly, there's another set of folds which have a different plunge and different versions, and those are these east-northeast plunging folds that are kind of tucked away on the limbs of some of these southeast plunging folds. So we've got an example here and another example over here. And now if we just kind of zoom into that area there and look at the geometry of those folds, well, this is what it looks like. We've got these large D2 or F2 folds that plunge towards the southeast. They verge towards the southwest. Here's another example in here as well. All of these southeast plunging folds with these east-northeast plunging folds on their limbs, which clearly have a different vergence. So what I've plotted here in the stereo nets, the large stereo nets are the poles to bedding, which have allowed me to determine the fold plunge of each of these different domains. But we won't go into that into too much detail. Just important to note that these smaller stereo nets where the cleavage, the S2 cleavage is clustered, well, the average of those clusters is pretty much the same for these southeast plunging folds as well as these east-northeast plunging folds. So both of these sets of folds have a common axial planar cleavage, which is the S2 cleavage. And we'll discuss the significance of that. On the Macmillan's Mountain, pretty much all of the folds plunge towards the southeast. So the same kind of principle here, different subdomains along fold axes. But the one thing to note is that the folds on the Macmillan's Mountain are a lot more non-cylindrical, i.e. their axes are very curvilinear. So for a fold like this anticline here, in this domain, plunging with a very shallow plunge, almost horizontal, along the axis, it starts to steepen to about 40 and then eventually to 70. So you've got these very curvilinear hinges. Yet the S2 cleavage also plots in a cluster, the average of which is 333.90, so pretty much subvertical on this mountain. And that's just a 3D sketch of some of the structures. Like I said, we've got these very curvilinear folds, F2 folds, that change, the plunge increases along the axial trace. Okay, so I won't go into the stereo nets too much, but basically the fold plunges are all roughly towards the southeast. There are quite a number of subvertical faults which have exploited the limbs of these folds. So this Rosh Pinah fault, a number of faults here, and Klipnia's fault up towards the east. So that's the general geometry. Some more D2 structures, also a little bit localized. On the Macmillan's Mountain, we've got some boudinage in some of these carbonate layers, in some very steeply dipping beds. So here, this is a kind of a dolomitic unit that's been boudinage. We've got nice angular asymmetric boudins with some layering S0, kind of that orientation, and some shearing, some synthetic slip that's occurred along these interbudin surfaces. That's what I've tried to demonstrate over here. And clearly, we've got sinistral kinematics here. So, by the way, this is a plan view. Budin axes are pretty much subvertical, and so the kinematics will obviously roughly be sinistral shear along this fold limb, with caused through west, northwest, east, southeast shortening, and north, northeast, south, southwest stretching. So, some more budins. Here's another train of budins. This budinaged dolomite unit that's encompassed by this less competent carbonate. If we zoom into that area there, we can see the budins have also been rotated. You can see some of the layering in the budins there. Synthetic slip along these interbudin surfaces. Some of these small antithetic faults in between, but the same kinematics as you would expect. Moving on to late D2 structures. Well, the late D2 structures are faults that cut across some of the fold limbs, as well as some of the D2 fold hinges. And these are quite frequent in terms of their spacing on the eastern side of the Macmillan's Mountain. So this is the eastern part of the Macmillan's Mountain here. In red, we've got these quite closely spaced subvertical faults, which offset units in the limb as well as the hinge, and some conglomerate marker units as well. So these are subvertical faults that have utilized the S2 cleavage, and the displacement has been calculated from offset marker beds, bedding drag, slicken lines, and things like that. So good kinematics on these faults. In plan, the apparent displacements are between 15 to 50 meters. So that obviously represents the minimum amount of displacement, because these are actually oblique sinistral faults. This is what one of these faults looks like in the field. Over here, you can see some bedding drag of these quartzites. Here's just a hammer for scale. North is sort of towards the bottom. So we've got some bedding drag. Along the fault, sometimes you find these small releasing bend duplexes. There's a plan view of one of them. Sinistral kinematics, you can see. This is one of the fault walls exposed, some nice slicken lines. And then moving on to the D3 stage of deformation, well, that's really recognized by the deformation of the S2 cleavage. And it's kind of manifested in different ways. In that quartz cerussite schist unit that I pointed out in the one cross section, you get these small shear zones that deform S2 as well as a bedding. So this is a bedding contact between a coarser grained and a finer grained arcos that have been altered, and you get these small crenulation kind of shear zones that crenulate the cleavage, the S2 cleavage. Very rare cases, you get some buckling of S2 cleavage. Here's an example of that. So there's S0. Okay, well that's actually a plan view. And this is the S2 cleavage that's been buckled, along with the bedding. Outside of these alteration zones, sometimes you do find contractional kink bands, so like these conjugate kink bands. Here's one set, and here's another set here. This outcrop, you can also see a conjugate pair of on-echelon vein arrays. Over here and here, and from the obtuse bisector of these kink bands and the acute bisector of the veins, we can work out the principal shortening direction. But I won't go into that in too much detail. But just to note that this is how D3 is primarily recognized. So moving on to strain analysis. Some strain analysis was done from samples and outcrop orientated photos of some conglomerate units, particularly these elistostrom units that are found in the Valacral Formation and also the diamictites in the Cargas Formation. And here's an example of what the Valacral Formation elistostromes look like. Very large carbonate blocks. You can see some quartz pebbles in there in this sort of arcosic matrix. So two class populations were, or data from two class populations were collected, analyzed the quartz grains, in some cases quartz pebbles, and also the large carbonate class. So to analyze the quartz grains, that involved taking orientated samples from different outcrops and cutting large thin sections of 3 orthogonal planes, and then scanning that data in and processing it. To analyze the carbonate class, well, that was really taking photos of orientated faces. We're trying to find roughly 3 orthogonal faces where possible, photographing them, obviously with the scale bar, etc., and the orientation of the face, putting that data into SPO and ellipsoid imaging analysis programs, and then calculating out the overall ellipsoid for each locality. So here's an example of 3 roughly orthogonal faces where you can see some of the deformed carbonate clasts. So in the end, we were able to plot up the ellipsoids. Here is some of the ellipsoids, well, really just the ellipses representing the long and short axes of the ellipsoid for various locations on the Roche Pinot Mountain. Most of the data obviously came from this Valacral Formation, this very coarse-grained sedimentary rocks. You can see these white ellipses are for the quartz grains, the grey ellipses are for the carbonate class. The carbonate class obviously more highly deformed because less competent. So most of these ellipsoids plunge between sort of 10 degrees to up to about 50 degrees towards the northwest, sometimes towards the north. So yeah, basically within the S2 cleavage. Unfortunately, fewer samples on the Macmillan's Mountain because there's just that kind of small outcrop of diamictite on the east of the mountain. But same kind of pattern, the ellipsoids plunging towards the north-northwest. Yeah, you can notice a bit of a trend in that the ellipsoids do plunge slightly more steeply on this Macmillan's Mountain. So although the strain doesn't really increase or decrease across the zone, this outer zone, but the plunge of the overall ellipsoids does kind of increase towards the east, towards this Macmillan's Mountain. Sorry. So if we plot up everything on a Flynn diagram, well, we've got the axial ratios of the long to intermediate axes on this axis plotted against the intermediate to short axes on this axis. One representing a sphere, and we've got this line of plane strain which separates the area of apparent flattening from the area of apparent constriction. So anything that plots here is going to sort of have a ellipsoid shape like a rugby ball, and anything that plots here is going to have more of an oblate sort of pancake type shape. You can see the quartz grains plotted with these round circles. The carbonates are these diamonds here. these tile lines are where the data was taken from the same outcrop. And we can see that most of the samples actually plot in this field of apparent constriction. It's a little bit strange because we've got quite a strong S2 fabric in this area. So one would expect more of like an oblate strain. But we do find some samples plotting in this field of oblate strain. And okay, we'll talk a little bit more about what that means later. Okay, so just going into a discussion now. It's been known for a long time that this Gariep belt was deformed by a sinistral transpressive event, which was a result of oblique collision between two rotating plates, or kind of a subplate and then part of the Kalahari craton. Now, transpression is not merely in terms of plate, it can't really be explained in terms of plate trajectories, but more in terms of kinematics, how a zone actually deforms. So, a very famous sort of work that was done describing transpression in a kinematic sense described it as a homogeneous monoclinic deformation consisting of orthogonal pure shear and simple shear components. So you have a zone which is basically experiencing shortening along this y-axis and shear along this x-axis simultaneously. So this is sort of like the first kind of working model. But since then, a lot of other derivatives of this model have been explored with different zone boundaries, kind of movement along zone boundaries and different dips of zone boundaries, etc. So without going into too much detail about that, it's just in terms of understanding how the Gariep belt actually deformed, it was necessary just to examine some of the components that one needs to understand when looking at a transpressional zone, which are the orientation and nature of the zone boundaries, the geometry of structures within a transpressional zone, and orientation of foliations. Now, the zone boundaries, which are defined by the contact with the basement as well as this ice road fault, are actually both dipping inwards towards the actual wedge that's being deformed. And the ice road fault, the kinematics are not too clear, but the basement Gariep cover sequence contact is a notable thrust zone. And because of these dipping zone boundaries, we've got to look at an inclined transpressional model, and quite a lot of work has been done, describing inclined transpression. But basically, what happens in an inclined transpressional zone is that the zone experiences simultaneous contraction, strike slip, and dip slip shearing. And the result is that you find a foliation that's generally oblique to the zone boundaries, and you find a stretching lineation or mineral lineation, in some cases, that's kind of plunging obliquely. And inclined transpression is quite common with these obliquely convergent settings. All right, geometry of structures. Well, as I've already explained, we've got these southeast plunging folds that verge towards the southwest, and on their limbs we've got these east-northeast plunging folds, which not only do they have a different plunge, but they've got a different vergence, so they verge towards the southeast. Now, it's impossible to form this kind of geometry with contrasting vergences like this simultaneously during transpression. So the interpretation is that these east-northeast plunging folds, because they don't have an associated S1 fabric, but they have an S2, or the S2 fabric is axial planar to them. They interpret it as composite structures that began during D1 and then were modified and transposed into the S2 axial plane. Carrying on with the geometry of structures, like we've said, these southeast plunging folds have these curvilinear hinges, while having a very consistent S2 axial plane, which is seen by the consistent cleavage. So this is sort of just an example of like one of the anticlines that has about a 65-degree plunge change along the axis. So the interpretation is the variation of the fold plunges is not due to D2 deformation of D1 undulations, nor is it due to later D3 deformation, because we don't find, with this kind of variance in plunge, you might expect a D3 fabric, so like an S3, but we don't find that. So because of the lack of any S1 cleavage or any S3, the interpretation is that this curvilinear nature, the non-cylindrical nature of these folds, actually originated through transpression, and this is actually sometimes quite a common feature within transpression, because of the basically the three axes of the finite strain ellipsoid are continuously rotating because of this triclinic strain. So you've got the strike slip and the dip slip shearing and contraction at the same time. So it can produce these curvilinear folds within one event. So we believe that this happened during the D2 phase. Again, the trend of the main fabric, the S2, is oblique to the zone boundaries. So you can see the S2 averages sort of for these two different mountains are quite oblique to these zone boundaries, which reflects the strike slip component in this sinistral transpressive event. So this obliquity in the foliation can be explained by the sinistral transpressive event. The dip variation of S2 also needs to be explained. So like we've said, this Roche Pinot mountain, the folds verge towards the southwest. We've got this moderately dipping cleavage. To the east, the Macmillan's mountain, we've got these upright folds and the subvertical S2 cleavage. So the interpretation of this is that there was strain partitioning that occurred across this outer marginal zone based on some of the rheological properties of some of the rocks in the Port Nolloth zone, namely this thick rhyolite package of the Spitzkop Formation, very sort of competent body in a sense, subvertical boundaries, and you would out towards the east, of course, have the contact with the basement. So the interpretation here is that strain was partitioned into a western domain dominated by dip slip, non-coaxial shear and flattening strains, and an eastern domain out here, which is more pure shear dominated because of the subvertical rhyolite body and the contact with the basement towards the east. The orientation of the clasts, or the plunge of the clasts, is a lineation which is part of the rock fabric. And through a lot of studies, it's been shown that inclined transpression can produce obliquely plunging lineations, whether it's clasts or mineral lineations, through one transpressive event. It need not be overprinting through multiple different deformational events. And so the interpretation here is that the plunge of the strain clasts across this area was attained through during the D2 event, which was the main part of this sinistral transpressive event, and not as previously thought through reorientation of the clasts through different events, one overprinting the next. So the structural evolution, so this is kind of a summary now of the evolution of the deformation. And basically this study has simplified the deformational history quite a lot, and not necessitating a lot of complex reorientations of the principal strain axes. So, okay, there has definitely been some reorientation of principal strain axes, but not as many kind of events as was previously thought. D1 was a northwest-southeast shortening event, which was associated, or which caused thrusting, and these F1 folds that now are preserved as these east-northeast plunging folds on the Roche Pinot Mountain, which I tried to show here, as well as some F1 folding with some S1 fabric in some very localized areas, mainly due to lithological properties, like in the carbonates on Macmillan's Mountain there. So D2 was the main phase of deformation. So there was this kind of anti-clockwise rotation of principal strain axes, and during this phase, strain partitioning, so a western domain which became dominated by dip slip, non-coaxial shear and flattening strains, producing these asymmetric folds and this dipping cleavage. An eastern domain which is more pure shear dominated, where these upright folds formed pretty much a subvertical S2 cleavage, and during this D2 phase, at the same time, we had these curvilinear hinges that were developing, and the plunge of the strain clasts was basically attained at this phase of during D2. So D2 was really when most of these main kind of structures that are manifest kind of formed. Then mid to late D2, there was more localized strain partitioning, mainly in this pure shear dominated, or in this zone to the east, where we had oblique sinistral slip faults offsetting some of the fold hinges here, with further fold amplification occurring. And then during D3, this is on the Roche Pinot Mountain, just try to show some of the deformation of the S2 cleavage, some buckling of S2 cleavage in very localized spots, some of these crenulation cleavage zones, conjugate kink bands, etc. All right, so in summary, the outer margin of the Gariep belt was formed through a sinistral transpressive event with at least 3 fabric forming phases. D1 involved northwest to southeast directed shortening with some accompanying folds that are preserved in the Roche Pinot Formation, and some minor folds in some of the carbonate lithologies. D2, the main part of the transpressional event, which resulted in most of the large-scale folds and the dominant S2 fabric. Strain partitioning occurred during D2 progressively over time. So initially it was more larger scale into a western and eastern domain, and later into the eastern domain was further partitioned So that happened during late D2 with these oblique sinistral faults that started offsetting some of the fold hinges, and then finally D3 where strain axes were more inclined, and so that phase of deformation is mainly just recognised, as we said, by localised deformation of the S2. Thanks for bearing with me. I know it was quite long. I had to fit quite a lot into 1 hour, or I don't know how long it took. Maybe time's flying. We've been here for 2 hours. I don't know. Yeah, so any questions, please feel free.
Right, thanks so much, Matt. That's a really detailed talk. Are there any questions? And if there are, can I ask you to speak loudly so that people on YouTube can hear me? Roger, loudly.
Thanks, Matthew. Your initial diagrams showed essentially a two-dimensional cutaway with thrusts and what have you, thrust packages from essentially west to east. How does this zone fit in? Do you think it's simultaneous, or have you actually seen a package develop and eventually everything gets concentrated at this margin?
Well, this was actually a bit of a sort of limiting factor in that most of the formation bounding faults which we envisage where the large thrusts are subvertical, and we can't really constrain the kinematics on them too well. So basically my understanding of it is that these large formation bounding faults that are now subvertical where the major thrusts, there are some sort of minor thrusts that can be picked up within like the Roche-Pinot formation. And then later on in the transpersonal sequence, we have these faults recording this oblique sinistral or sort of like sinistral reverse movement. So both the large-scale formation bounding faults as well as these faults that cut across the formations, and that sequence of deformation, the kinematics can be seen quite well on these faults. But unfortunately, probably the initial thrusting that happened during the D1 phase, you kind of really have to just assume when we look at these formation bounding faults, because they're now so vertical and you can't really pick up the kinematics too well of the initial thrust movement.
Other questions? Paul, nice and down.
Fascinating, Matthew. You mentioned basin inversion at one point. Is there any evidence that your thrust faults were originally basin margin faults, potentially with a controlling influence on the mineralization?
Well, definitely the basement cover sequence, that fault is like a bounding fault, that original kind of failed rift, and some of the formation bounding faults as well. Look, there's not too much evidence in the field that these were some of the initial faults that were reactivated, become these compressional faults. But yes, that sort of inversion from the extension to compression it's kind of more in the literature, and it's, I think, from the regional work that's been done by Elkin and some of these guys, that's how it's been explained. But I wouldn't really be able to say with too much certainty whether this specific formation bounding fault has been inverted or whether it was just a thrust. So I couldn't really find so much evidence of the inversion. But yeah, I mean, unfortunately, just with the time, I wasn't able to talk too much about the mineralization because I was also part of the project, looking at some of the 3D geometry of the ore bodies underground, relating them to the structure on the surface. So hopefully that can form part of another talk. I think that would be of interest economically for those of you who are interested in that kind of thing.
Axel,
Why did you compare the strain of the quartz grains with the strain in those large pebbles? I mean, to me it looked like some extra work for you. I mean, you already did lots of work here.
Yeah, that's a good question. Well, to be honest, it didn't really yield anything like that was too sort of extraordinary. But basically, we just wanted to see if we could compare more like the carbonates and the carbonates, from different localities, because, and the quartz grains with the quartz grains from different localities. So at some localities, I only collected data relating to the quartz pebbles, and other localities only the carbonate class data. Some localities both. It was just depending on what I could get from specific outcrops. And it was like an awesome idea at the beginning, but it didn't really yield, something new and groundbreaking. So.
One last question. Yes.
You showed us this quartzite and this kind of deformation of kink bands. You mentioned granulation,
Yes.
but I'm not sure. I don't know the quartzite here. So, are there a lot of platinum minerals inside the quartzite which can give you some kind of granulation, or is it more like something which might be even developed in an earlier stage, like deformation bands? Because it looks very narrow to me.
Yes.
And for the kind of rock, it's somehow weird to see those kind of.
Okay, so it's actually a quartz sericite schist. So it's basically an alteration of an Arco's protolith. So I think it's basically that late D3 crenulation of the S2 occurred, in those nicely spaced bands, only in the alteration zone, just because of the plating minerals in that basically sericite in the sort of altered arcos. I mean, all of this is green schist facies deformation. That's why I sort of omitted the meta, just called things arcos, argillite, etc. Those alteration zones are just very localized and kind of slightly different. So there's probably a bit of fluid flow happening there that could cause those localized alteration zones. But yeah, as it turned out, good place to recognize D3.
All right, thank you very much once again, Matthew. That was great. All right, so here you can see the next few talks for the upcoming weeks. Next week we have Katie McFall from Cardiff speaking about primary volatiles in layered intrusions, specifically from the northern limb, I think. And then the week after that we have Max Hash on shatter cones. So please join us for that, or if you can't make it, come and join us on YouTube. You can follow these talks now on YouTube. So thank you very much to John Hancox from CCIC Coal for the drinks and chips.